This is a short introduction to imaginary numbers. A little bit of background. We've said this a bunch in the last couple of weeks. If you're asked to find the square root of negative 4, we've said that negative 4 doesn't have a real root, or a square root, because there's no number that can be squared to make a negative. Right? If you try and take negative 2 and square it, it's not negative anymore. So what could you possibly square to make a negative number? Well, we lied. There is one number whose square is negative. It's called I, the imaginary unit. It's the one number that if you square it, it's actually equal to a negative. Not just any negative, it's equal to negative 1. So I squared is equal to negative 1. Which means that the square root of the square root of negative 1 would be equal to I. The number that if you square it, it equals negative 1. Well, that means that any square root that has a negative in it can be simplified. It's called imaginary numbers. That doesn't mean they don't exist. I don't really like the name imaginary. It makes it sound like they're nothing, but they are. They're something. They are imaginary numbers. So, the key that you have to remember is if you want to simplify a radical that has a negative in it, like the square root of negative 9, you have to take the I out first. Once you take the I out, the imaginary unit out of a number, you can simplify the rest of it. So what I'm going to do is take the square root of 9 and think of it as the square root of 9 times the square root of negative 1. Because both of those two parts separately I can simplify. The square root of 9 is 3, and the square root of negative 1 is I. So the square root of negative 9 is 3i. If you take 3i and square it, you get negative 9. Promise. We'll look at a couple more examples just so you can get the hang of it. So if we look at number 5 here, the square root of negative 8, this works for numbers that aren't perfect squares too. So just like we would simplify any number, any irrational square root by taking out the perfect square, we can do that for a negative number also, as long as first we take out the imaginary unit. Take out that I first, separate the 8 from the negative 1, and now I can simplify the square root of 8 the same way we've been doing so far this unit, and simplify the square root of negative 1 to I. So this becomes 2 times the square root of 2 times I. We do write it in this order. We don't put the I in the middle there. We don't write it like that. We put the I at the end. And for number 6, same idea. I can take the square root of 125x to the 5th and separate it from the negative 1. And once I've done that, I can simplify the square root of 125x to the 5th in the usual way. Take out the perfect square, divide the exponent of that power in half, leaving the remainder alone, turn the square root of negative 1 into I. And I'll pull my x squared away from the radical so I can put the 5 and the x together, and that would be your answer. 5x squared times the square root of 5x, I. Another type of number, it's really the same type of number that we've always been dealing with, is called a complex number. Possibly you've never heard this term before, but all the numbers that you've ever dealt with in your life, they've been complex numbers. Complex number just means any number at all on the planet, whether it includes real numbers or imaginary numbers or both. And complex numbers are written in the form, we call it a plus bi form, where the a is the real part and the bi is the imaginary part. So if you have a number 6 minus 7i, we would say the a is 6, the b is negative 7. This a plus bi form is going to be important to us because every time we have a number that includes an imaginary part, we have to write it in a plus bi form, even if it looks like we don't want to. For example, if we have some complex numbers and we're trying to divide them, 5 plus I divided by 2I. Just like we don't want a square root in the denominator, we only want rational numbers in the denominator. And I, it's not real, so it can't be rational, because rational numbers are a type of real number. So we need to make that the denominator, be rational. We need to get rid of the I. All we have to do is multiply this fraction by I over I. And what will happen to the denominator, 2I times I is 2I squared. And you might be thinking, wait a minute, that didn't make it better. Now there are just more i's in the denominator. But I squared is -1. That's the definition of I. So we can, every time we see an I squared, we just immediately turn the I squared into a -1 and just change the sign of whatever term it's with. So that 2I squared is just -2. And now there's no longer an I in the denominator at all. In the numerator, you do need to be careful. It's very easy to forget about this here. But that 5 plus I is grouped together in parentheses, so you do want to make sure you're looking out for that. We have to distribute the I to both terms. And that I squared I was just talking about, it appeared again in the numerator. Remember that I squared is -1. So we'll have to change that. And we're done simplifying everything, but we don't leave it like this because, like I said a minute ago, every single time we have an imaginary component to a number, we need to write it in a plus bi form. Have to. So what we're going to do is take the 5i minus 1 over to -2 and separate it into two separate fractions. First fraction with the real numbers, that's the 1 over 2. Sorry, -1 over -2 is 1/2. And then we're going to separate that out from the imaginary part, the 5 over -2, because the negative, there's only one negative there, it doesn't cancel out. So we'll have minus 5 over 2 times I. And that's what we call a plus bi form. And this would be your final answer. For the next one, 3i over 2 plus 4i. Similar idea. We just don't like that I in the denominator. So we have to get rid of it somehow. But multiplying by I over I won't help in this case. Don't write this down in your notes because I'm about to erase it. If we were to try to multiply by I over I, we would distribute that I to the 2 and to the 4i. And sure, this would become 4i squared, and that's great because that I squared becomes -1. But the 2i doesn't really help us. We've just moved the I over, so that didn't do anything. What we're going to do instead is use the similar strategy that we did for rationalizing with square roots, is multiply by the conjugate of the denominator over itself. Remember that word conjugate? What makes two binomials conjugates is if their middle term is opposite. And I will write down that word conjugates to make sure you see it spelled out again. And the power of using conjugates is when you do multiply them together, they make only a difference of perfect squares. So we'll have 2 times 2 minus 16i squared. If you're worried about the middle terms with foiling, you don't have to write this down, but think about what would have happened if we would have foiled it all out. 2 times 2, 2 times -4i, 4i times 2, and 4i times -4i. What's going to happen with that middle two terms is because one's positive and one's negative, they'll have the same coefficients, but they'll be opposite signs, so they'll always cancel each other out. And so that denominator will have 4 minus 16i squared. But of course, again, that I squared, it goes away. It just changes the sign of the 16, but it doesn't do anything else. So that denominator is now a nice, simple, rational 20. In the numerator, we are going to distribute. So that's 6i minus 12i squared. And again, we see this I squared. And again, every time you see that I squared, all it does is it changes its own sign. So we have 6i plus 12, which I can't really simplify that, but what I can do is rewrite it so that the real number is first. And then again, remember that a plus bi form, we are going to chop that up into two pieces. So I can do 12 over 20, which I'll reduce as I go. 12 over 20 is 3/5. And 6 over 20 is 3/10 times I. So that's my a plus bi form. So again, it's not a final answer until it's in a plus bi form. A couple more small things I want to show you before the video is over about imaginary numbers. First is a little bit note about just multiplying two of them together. So let's look at number 7. The only rule you have to know about multiplying imaginary numbers is that the only imaginary numbers you can multiply together are I and I, which is not a problem at all for number 7. The 2 times the -7 I can multiply. The I times the I can multiply. Great, -14i squared. And like what we just saw on the last slide, that I squared immediately just vanishes itself away. I squared is -1. So as long as we change the sign of the 14, we've got it simplified. It is a little bit trickier. You've got to be a little bit more careful for ones that look awfully similar. The square root of, let's go with -3 times the square root of -6. It is very tempting to say, oh, why don't I just multiply -3 times -6 and call that 18? It's very tempting, but it's just not true. That is not the answer. The square root of -3 times the square root of -6 is not the same thing as the square root of 18. Because you cannot multiply those two imaginary numbers together. You can only multiply I and I. So what we're going to do is pull the I out from both of these. And now that my radicals, the two square roots there, √3 and √6, they are real now, I can multiply them. And the two imaginary units, I and I, I'm allowed to multiply those. But now you can see why this makes a difference. The I squared is -1. So this is negative times the square root of 18, not positive times the square root of 18. And of course, I will simplify the square root of 18 while I'm here. To -3 times the square root of 2. And that is your final answer. Makes a big, big, big difference that I did not multiply those two imaginary numbers right away. First, I pulled the I out before I was allowed to do that. The only other thing I really want to show you before this video is over is not particularly important, but it gets asked about a lot. I don't know why math teachers love this so much. When you raise I to higher exponents, the higher exponents will never survive for very long. And let's see some examples to see why. Well, obviously I by itself is just I. I squared, we've already seen what that means, but just to make it really clear, it means the square root of -1 times the square root of -1. Of course, if you take a number, a square root, and square it, the square radical cancels out. So we'll be left with just -1. Truth is, I didn't need to explain it that way. I could have just said the definition of I is that I squared is -1. But let's take a look at some higher powers. So far, we've seen all that already today. But if we look at I cubed, if I rewrite that, sorry, not the square root, if I rewrite that as I squared times I, right, that's I cubed. Well, I squared is -1. Sorry about that, right? -1 times I, which is -I. And again, we started with the higher exponent, but it didn't last long. I to the 4th, similar idea. If we think of that as I squared times I squared, well, that's -1 times -1. And so those two negatives will cancel out, make +1. It's almost like the I, the imaginary unit, the square root of -1, it's like half of a negative. So 2 halves of a negative is 1 full negative. 4 halves of a negative is like 2 full negatives, which cancel out to make a +1. And then what's going to happen after this? I'm going to highlight these. to make that so big. What's going to happen as I multiply by higher powers of I is every time I have 4 i's, I can just pull them out, because that's 1. So eventually, it just gets ignored. So that becomes 1 times I, which is I again. And I to the 6th, I to the 6th is I to the 4th times I squared, which is just 1 times negative 1. I to the 7th is I to the 4th I cubed. And again, that I to the 4th, it just goes away because it's 1. So we're just left with I cubed, which is negative I. I'm not sure why I don't have it on here, but if we would go one step further, I to the 8th is I to the 4th, I to the 4th, which is just 1 times 1. So again, we have that same pattern of I, negative 1, negative I, 1. I, negative 1, negative I, 1. That pattern keeps repeating itself over and over and over again. So if I have a much, much, much bigger exponent, like, say, I to the 35th, all that means is a bunch of I to the 4ths, and there happens to be 8 full I to the 4ths here, but I don't really care. What I care about at the end is when I'm done, all of those I to the 4ths are all going to be 1 anyway, and all I really care about is how many are left over. So if I take 35 and I try to make groups of 4 out of it, I can get up to 32, but then there are 3 left over. So all that matters in the end is that leftover 3, which we know from our chart up here is equal to negative I. So this whole thing is just negative I. If I had a bigger one like I to the 74th, well, I to the 74th, it doesn't matter how many times 4 goes into 74, but it doesn't go in evenly. It gets up to 72 evenly, and then I'm left with 2 left over. So the I to the 72 cancels out to 1. All I'm left with is I squared, which is negative 1.